So let's see like how we can define like a simple architecture. For example, if we consider this CNN, we have seen this architecture before. It takes image as input, and then we have like several convolution layers, subsampling layers, and finally fully connected layers, and then the prediction. So let's try to define this network using PyTorch. And this is like the whole code I'm showing you at once, but I will go through this one by one. But if you clearly, if you try to skim through this, you can see like you have a class, you have the name of the function, and some of the things which we discussed. And this is the initializer. This is the forward function. We will talk about like what we have in initializer, and again we'll talk about forward function. And this is just a helper function which we need, I think, in the forward function. Okay, so this is like how standard neural network architecture looks like. And this piece of code is actually defining this architecture over here. Okay, so let's try to understand each and every line of this. Let's start with the initializer. So again, as I said, this is like standard Python. Don't worry about this. Now in initializer, what you do is you define your layers, which will be used by the feed forward function. All right. So whatever layers you want to use in your forward function, you will have to first define in PyTorch. Okay, and it will vary from framework to framework. For example, like if you're using a Keras framework, in Keras you don't have to define these. Okay, you can just use them like which are available in the framework itself in the forward function. In PyTorch, it's slightly different. You have to define this first, and that's actually good because if you have to modify like some of those layers, and you want like some kind of flexibility in defining the layers. So since you are defining, so it's actually good. But if you're sure that you don't have to do some advanced like architectural modifications, in that sense, Keras is actually much better than PyTorch. But again, it's kind of subjective discussion. So let's not go in that direction. So what we do, we define all the layers which are required in the forward function, and this is one of the convolution layer which will be used later on. And this is just like the name of the layer. Okay, we say that as con1. That's the name, and this is actually defining that layer. So NN is the function, the package which we imported from PyTorch. Con2D is 2D convolution. Okay, so we are defining a 2D convolution layer here, and it has 3 parameters. So let's go over like what these parameters are. The first parameter is the depth of the activation map coming from the output of the previous layer. Okay, and since this is the first layer, it's actually not the first layer in the initializer, but we are going to use it as a first layer in the forward function. And again, since we are designing that, we know that. So we are going to use this con1 as the first layer or the input layer. Then we know that we are designing this architecture for grayscale images, right? And grayscale images, we know that the number of channels, it's just 1. And the spatial shape is 32 cross 32. Okay, that's the resolution, but it's a grayscale image. And that's why we put this as 1. Okay. So the second is how many kernels you want in this current layer. All right. So this is 6, which means that this convolution layer will have 6 different kernels. Okay, so far so good. The third parameter is defining the shape of the kernel. Okay, so 6 kernels, and it's saying 3, which means you're not worried about like the shape of the kernel. So by default, it will be a square kernel. So if you say 3, it implies 3 cross 3. Okay, you could have written like 3 cross 3 explicitly here, which is also fine. But if you're just saying 3, it's 3 cross 3 kernel. So what this line of code did is you have now a layer which is named as con1, which is a 2D convolution operation. The input to this layer will have like some kind of activation map, which has depth of 1. And this layer will have 6 kernels, and each kernel will have a shape of 3 cross 3. Right? So far so good. Then let's define another convolution layer. The name is con2. Again, it's a 2D convolution layer. And it's saying that whatever activation map is being passed as input to this layer, it will have a depth of 6. And we are saying 6 because then the idea is we'll use this layer after con1. and con1 has 6 filters, right? If you have 6 filters, then the output at activation map will have depth of 6. And that's why the input to this layer will have a depth of 6. 16, we want to use 16 kernels in this layer. And again, 3, we want to use kernels of shape 3 cross 3. Okay, so that's good. Now, let's try to add like a fully connected layer. And this is just like a flattened fully connected layer where you have to define like how many neurons you want. So again, this is FC1 is just a name. And the library function you have to call is nn.linear. Okay, so this is called linear layer. And let's go through the parameters. So if you think about fully connected layer, it has some set of it has some set of neurons, right? And it will receive like again a set of neurons, and then depending upon that, you will have certain set of weights, and you will do linear combination of each of the neurons to generate the output. Okay, so this linear layer has 2 parameters. This is the first one, and this is the second one. Okay, so before going to the first one, this is slightly complicated, but not that difficult. And I think this answers the question one of you were asking when we were starting the lecture today, right? So let's go over the second parameter first. The second parameter says in this fully connected layer, you will have 120 neurons. Okay, simple. So you'll have 120 neurons. Now, this first parameter is saying how many neurons you have in the previous layer. Okay, so it could be any number, but I will come to that, like why we have 16 cross 6 cross 6. So this is like the total number of neurons in the previous layer. So now you have neurons in the previous layer, you have neurons in the current layer. You can just multiply these two to get like total number of parameters you need for this layer. All right. So now let's talk about how you get this number 16 cross 6 cross 6. So it will depend upon a lot of things, basically 2 different parameters. Okay. The first parameter will be, because before this, we have a convolution layer, and you know that output of a convolution layer is like a feature map. Okay. It will have a cuboid shape, X and Y, that's the resolution, and it will have a depth. That depth will depend upon how many kernels you will have in this convolution layer. Right. So you can see that in the previous convolution layer, we have 16 kernels. So which means that the output of this con2 will have depth of 16. That's why we get the 16 here. Okay. Then these are X and Y, which is like the resolution of the activation map. So since it's a cuboid, and to feed it into the fully connected layer, you'll have to flatten it, which means you will have 16 times 16 times 6 times 6 neurons in that feature volume, which is exactly like the number of neurons you need in that layer. Okay. Now the question is how you got 6 cross 6. And again, so this second term will depend upon what is the input of your image. And you know that given an input image, if you are performing convolution, then you are going from volume to volume. And if you don't use any padding, and if you, depending upon like what stride you have, what padding you have, the shape of the output volume will change. Okay. So in this case, we're not talking about padding and stride at all, which means like we are just using the default values. So whatever shape the input image will have, let's say it's 28 cross 28. After this con layer, it's just saying that the shape will be 6 cross 6. And that's how you compute the number of neurons in the previous layer. All right. Now let's define another fully connected layer like this. So again, the name is FC2 nn.linear. And this is number of neurons in the previous layer, which we know is 120. And 84 is the number of neurons we want to be in this particular layer. Let's say 84. And we have one more fully connected layer, which is FC3, again, nn.linear. And again, 84 is like number of neurons in the previous layer, which we know is 84. And 10 is like in the current layer, which says that this could be the classification head. And we want 10 different predictions. So this 10 comes from that. Okay, so this is the initializer, and this is just defining these layers. Now, we will use these layers to actually construct the architecture, and that will be done in the forward function. So the input to forward function is your image X. It will have certain shape. For example, if it's a binary image, it could be 28 cross 28 cross 1, or it could be just 28 cross 28. Okay. Now, this is the first operation, and this is kind of a compressed writing, but don't worry about it, because you know that your layers are just functions, right? Whatever output you have from one layer, that will go as argument to the second function. So you can always write that as chain of functions, and that's what this line of code is doing. So let's start from the top. X is the input, and you're using the first layer, self.con1, which we defined in the initializer, right? So this will actually perform that convolution operation, which means it had how many? Six kernels, right? And 3x3. So whatever operation we know, like convolution layer will perform, that will be performed. And output of this layer is passed to a ReLU activation. So you can directly use like f.relu. Again, f is like functional API imported from PyTorch. So you can directly call this a ReLU activation, which means that this activation is applied on the output of your first convolution layer. All right. Then again, output of that activation is then passed to a max pooling layer. So this is how you call max pooling layer. Okay. So you don't have to define max pooling layer. And the reason is we know that max pooling doesn't have any parameters, right? And same is the case with ReLU. We don't have any parameters. That's why we don't have to define them in the initializer. Of course, you can define them and then again use it, but there is no point because we don't want to learn any parameters there, right? So then whatever output you have from the ReLU activation, you will perform max pooling operation on that. And you can see here that we have a second parameter, or you can say second argument passed to this max pooling operation. First was the data itself, and second is the shape of your kernel to be used for max pooling, which is 2x2. Okay, so I think 2 should be like the shape of the kernel. All right, so which will be like 2x2, and the second 2 is the stride you will use. So you will skip 1 pixel and then you move forward. So these are just parameters to your, or arguments to your max pooling function. Now, which means that let's say if your input is 28 cross 28, right? So convolution will, I think, change that to 26 cross 26, I guess, right? You can do the math, but just like a rough estimate how we got that 6 cross 6. So if the input is 28 cross 28, con will get it to 26 cross 26. ReLU won't change it. And max pool 2D, again, it's 2 cross 2 and stride of 2. It will give you, I think, 13 cross 13. All right. So it means that shape of this activation will be 6 cross 13 cross 13. 6 is coming from the number of kernels you have in this con layer, because neither ReLU nor the max pooling is going to change the depth of that activation map. Okay. Now, again, this output X of this max pooling is being passed to this con2 layer, which is the second convolution layer. And again, this is, I think you had 16 or something kernels, right? 3 cross 3. So that I think will give you again 12 cross 12 after this. So the shape will be 16 cross 12 cross 12. And then ReLU, it won't change the shape. And again, max pooling 2D, it's the same operation we did here. And you can see like the shape is 2 cross, the argument is just 2, which means I think the kernel size is 2 cross 2. So that 16 cross 12 cross 12 cross 12 will go to 16 cross 6, 6 cross 6. So this X will have a shape of 16 cross 6 cross 6. And that's how we got that 6 cross 6. Now what we are doing is, you know, that we are just trying to reshape, because output of this is going to go into a fully connected layer, and we know that fully connected layer, everything should be flattened. You can't send in like your a cuboid shape or something like that. Okay, so this view is actually is actually changing the shape of this X. The shape of X is 16 cross 6 cross 6, and it's trying to flatten it. So it's saying like the first dimension, I don't care, whatever it is. Okay, so now you know that what this -1 means. But the second argument is it's trying to compute the number of neurons in X. Okay, so this is a helper function, number of flattened features, which again we have written in this class, and it's doing nothing. It's just trying to count like how many values you have in that volume. So if this volume X is 16 cross 6 cross 6, it's a cuboid, right? We know that it will have 16 times 6 times 6 values. So this function will do nothing. It will just return that number. Okay. And this is going to be the batch size which you will use. So don't worry about this right now. But this will give you 16 times 6 cross 6. And then again, you will send that as input to your FC1. And you know that this one has, I don't remember how many neurons, but the input was 16 cross 6 cross 6. That's how we computed that. And again, you can have another fully connected layer. This X will go here. And then finally, you can make prediction. So at the end, this X stores like 10 different values. And each value will tell you whether that particular object category is present or not. Okay, so that's how you go from your image to making predictions about that image. And this predictions is going to tell you like whichever prediction is actually the highest, you will say, okay, this object category is present. And that's like a very simple convolution neural architecture. It has 2 con layers, 2 ReLU activations, 2 max pooling layers, and 3 fully connected layers. Okay, so it's not that difficult. You can see like a lot of code reuse is happening here. And then finally, this forward function will return X again, which is the prediction. So that was the helper function I was saying. So this piece of code is doing nothing. It's just trying to compute the number of neurons you need or number of values you have in that cuboid, right? So I can quickly walk you through this, but I think it's pretty straightforward. So this X dot size, again, you know, it will give you the size of that feature vector. And this is slicing, which means that you're ignoring the first axis, which is always the batch size. So you ignore this and consider all the other. So what will happen is if your batch size is, let's say 10, then the actual shape of X will be 10 times, 16 times, 6 times 6. And this size is going to return that, but this slicing is actually ignoring the first dimension. So size here, the variable size will actually store 16 cross 6 cross 6. Okay, and in this for loop, you're just actually multiplying those 3 values. And you just return that value. Okay, it's just a helper function, and you can have as many helper functions as you need in your architecture.